Hi, physics. Mr. Janowski here. This is the Chapter 13 Study Guide, Problem 4. So, what's going on here? Mars has two moons, Phobos and Deimos. There's the mass of Mars, its radius, and its average distance from the Sun. And let me just warn you right off the bat that many of those things are red herrings. So, lots of information about these things that seems like it might be useful that you're going to have to learn how to ignore. So, what are we trying to figure out here? So, for part A, Phobos orbits Mars with an average radius of that from the center of Mars to the center of Phobos. What is its period? So, what we're looking for is its period. So, what is the symbol for that? That is the big T. So, period, it's the length of time it takes the thing to orbit. It's a big, important time. So, we give it a capital T. So, T is equal to question mark. And what units will it have? Well, it's a time. So, we're going to measure it in seconds. And then for part B, Deimos has a period of that. What is its average distance from Mars? Again, center to center. So we're looking for the average distance. So what we're really looking for here is the radius of its orbit. So radius is question mark. And what units will that have? That will be meters. So let's begin. So if you wanted to, in part A, we're trying to find for period. So the ugly version of Newton's version of Kepler's third law, which is this: T is equal to big square root big parentheses, 2 pi over square root gm. Sorry, I'm copying this down as I look. Times r to the 3/2. So if you're really good at the calculator, you can do it this way, and this will just spit out the answer for t right away. That would certainly work, but I'm going to recommend not doing it that way. I'm going to recommend just ignore this version. It's a little too tricky to get into the calculator, and let's do this version. T squared is equal to 4 pi squared over gm times r cubed. So this is no picnic either, but I do think this is easier to get into the calculator than the first version, the ugly version. So again, this is just exactly the same thing, only I squared everything there to get rid of this square root on the bottom and to get rid of this r to the 3/2 power. So we have this, and this will work. The one thing is, at the end of this, we're going to get a number that is not what we're looking for. We're looking for t. This will deliver a number for t squared, which is fine. We just have to remember to take the square root at the end. So yeah, we'll use this version. So what do we have? T squared is equal to big square root 4 pi squared over big G, okay, 6.67 times 10 to the minus 11th times m. Okay, so here's the thing. There are a couple of m's here. Do we want the mass of Phobos or do we want the mass of Mars? Well, when you're using this formula, you always want to use the mass of the thing that is being orbited. So not the mass of the thing doing the orbiting. So we don't want this one. This is going to be a red herring. I'm not going to switch to red and circle it like a fish, but yeah, that's your red herring. We don't need to know the mass of Phobos. What we do want is this one, the mass of Mars. Okay, so yeah, the mass of Mars is 6.42 times 10 to the 23rd kilograms. So Mars is actually fairly small for a planet. It's way smaller than the Earth. So yeah, there's the mass of Mars. That's the mass we want to use. Now, what do we use for the radius? Do we use, the radius of Phobos? Did I even give you the radius of Phobos? No, I didn't. Do we use the radius of Mars? Do we use the radius of Mars's orbit? No, we don't. What we use is the radius of Phobos's orbit. So this number right here. So 9.38 times 10 to the 6th meters cubed. So that's what you want to do. So when you do all that in the calculator, you might want to take this step by step. There's a few ways to get this wrong. But if you do all this in the calculator, you're going to get a number that is, I'm just going to copy it down exactly, 7608619.8, apparently. How did I get a 0.8 in there? Whatever it was. Oh, yeah, because that was a decimal. Okay. And is this our answer for t? No, this is actually our answer for t squared. So this is something squared. So to get our final answer, what we need to do at the end of all this is take the square root of this. So the easiest way to do that, I mean, you can take this number, write it down separately, and then use the square root function. But the easiest way to do that is if you have this number in your calculator, just hit on my calculator, it's x to the box. So I have a button that looks like this, and then make it 0.5 or 1 over 2. Because raising something to the 0.5 power is the same thing as taking the square root. And if you take the square root of that number, what you're going to get is t is equal to 2.76 times 10 to the 4th seconds. Which is about 27,000 seconds. So step we solved for the right thing. We gave it the right units. And so we're happy with that. On to part B. So yeah, in part B, let me make it a little darker. In part B, we're trying to figure out the average distance from Mars. So what I would do is copy down the pretty version of Newton's version of Kepler's third law. So 4 pi squared over gm times r cubed. So the thing we're actually trying to solve for here is r. So I would first do the little bit of algebra that solves this for r cubed. And if you do that, you're going to end up with r cubed is equal to big G, big M, times t squared over 4 pi squared. So look at this guy right here and convince yourself that that little piece of algebra I just did worked. So I multiplied both sides by big G and big M, and then divided both sides by 4 pi squared, and I end up with this. And then I switched left and right just because that's going to make this easier to do. And so now we're going to plug in the numbers. So big G is 6.67 times 10 to the minus 11th. And then we're ignoring its units as usual. So what mass do we use? Do we use the mass of Deimos? No. Again, you always use the mass of the thing being orbited. And the thing being orbited in this case is Mars. 6.42 times 10 to the 23rd kilograms. And now we need t squared. So what is t? T is the period of Deimos' orbit. So that's going to be this number right here. So 1.09 times 10 to the 5th seconds. And remember, this gets squared. So this is a common place to make the mistake. But yeah, there was a squared over here, so don't forget to square this. And then on the bottom, we're going to divide by 4 pi squared. So yeah, there's lots of order of operations things to get right in this problem. So on the top, make sure you're only squaring this last term. You're not doing the whole thing and then squaring the whole top. You're only squaring this last term. And on the bottom, make sure you're dividing by 4 and then dividing by pi squared. Lots of ways to get that wrong. So you may want to actually do it kind of like this. An extra set of parentheses helps. You don't absolutely need them. I personally try to not use parentheses if I can avoid it and just get the order of operations right. But I have done thousands and thousands of these problems on my calculator, so I'm pretty good at doing these. If you're not, then just take it piece by piece. Maybe solve for the entire numerator, write that number down. Solve for the entire denominator, write that number down, and then divide the numerator by the denominator and get that number. So anyhow, If you do all this, you are going to get an extremely huge number. You are going to get 1.2887 times 10 to the 22nd. So is this our answer for r? No, this is not r. This is still r cubed. Remember, that's what we started with over here. So this is not something in meters. This is actually something in meters cubed. So what you want to do at the end is, again, take the cube root. So the easiest way to take the cube root is start with this number. Whoop. This number here. And then you're going to use the x to the box again. So x to the box. And then you can, to take the cube root, I mean, one thing you could do is you could do 1 divided by 3 would do it. You can just hit 0.3333 a few times. That'll get you close enough to the cube root, because raising something to the 1/3 power is the cube root, and 0.3333 is 1/3. So yeah, if you do all that to this number right here, whoop, what you're going to get is r is equal to 2.34 times 10 to the 7th meters. So put a box around it. And yeah, we solved for the right thing. We gave it the right units. And this is a more reasonable distance. So you give it a check. So hopefully you found that helpful.